Welcome back to the lecture on chapter 11. This is the beginning of part 3. We've just finished off ventilation, this topic, with the topic of obstructive sleep apnea, and we're about to transition to gas exchange. That's the third. It's one of the three of those major aspects of respiratory system: ventilation, gas exchange, and perfusion. So let's do gas exchange now during this third part. All right, so the gases we're talking about are always oxygen and carbon dioxide. Both of them can dissolve in water, and they can dissolve, diffuse right through the cell membrane, that phospholipid bilayer. So you don't have to transport them. They just spontaneously move down their concentration gradient. Because what we're talking about are gases, instead of saying concentration, we call it their partial pressure gradient. So pressure is the amount of force that's being exerted by all the different gases, and partial pressure is the part of all of that force that's being exerted by just the gas you're interested in. But again, if you need to substitute concentration in your head for that, use that. The big one, oxygen carrying primarily happens on this protein hemoglobin. Just a quick reminder. So the upper one, this is a diagram from our textbook. This is the simplified cartoon that I had used before. There's 4 main protein subunits. Each one of them has a heme group in it. And at the heart of each of those heme groups is an iron atom. And it's the iron atom that binds the oxygen. We'll talk about saturation of hemoglobin. When all 4 heme groups have oxygen attached, we say it's 100% saturated. If only 3 of them have oxygen attached, it's 75% saturated. All right, so let's talk partial pressures and saturation. Up here, you can see the hemoglobin saturation. Mostly what we deal with is hemoglobin that has either all 4 spots taken up by oxygen or 3 spots taken up by oxygen. In extreme cases, you may have it drop lower, but mostly we deal up here. So when we say deoxygenated blood, you can picture this, a hemoglobin. Most of the hemoglobins have 3 oxygens attached. Maybe some of them have 2. I'm not going to go into the details, but these are the partial pressures of oxygen in the different places in the blood. So an average hemoglobin saturation of about 75. This is venous blood. And again, I'm not going to go into that. So oxygenated blood. So the deoxygenated blood comes in, goes around the alveolus, and picks up oxygen and has higher oxygen saturation on the way out of this capillary. Then that blood arrives at the tissues. It's arriving from this side. That's the very highly saturated. Lots and lots of the hemoglobins have all 4 of the spots taken with oxygen. And the tissue has low amount of oxygen, low oxygen concentration, if you will. And so some of that oxygen diffuses off of the hemoglobin and diffuses into the blood. And so that's how we end up with the so-called deoxygenated blood working its way back to the heart. So let's see these 3 aspects again: ventilation, perfusion, and gas exchange. Ventilation, we're talking about breathing in atmospheric air to bring in more oxygen to the alveolus. Perfusion, that's bringing the deoxygenated blood from the heart and arriving in these alveolar capillaries. And then gas exchange is what happens here, having oxygen move from the gas in the alveolus into the blood and having carbon dioxide moving the other way. But we're not talking about carbon dioxide right now, just oxygen. All right, how are we going to assess oxygen levels? Well, there's a couple of ways. The non-invasive way to measure with pulse oximetry, and just put the little sensor on the finger. This is really cool. We don't talk about this in a lot in nursing, but what that's based on is actually the color of hemoglobin. The more oxygenated hemoglobin is, the more oxygens are stuck on those heme groups, the redder the hemoglobin appears. The less oxygen, it appears less red or a darker red. And so when we do pulse oximetry, we put the thing on here, we shine a light, and then there's a sensor on the other side detecting what color is most of this, what frequency is this light wave, or what's the wavelength of the light that's coming through, which is fabulous. It's not the most accurate way of measuring oxygen, and that's why we have this other way of doing it. It's an invasive measure. Since what we're interested in is what's going on in the arteries, in other words, oh my goodness, the blood picked up oxygen in the lungs, that blood got returned to the heart, then it got pumped out from the left side of the heart. That's the blood we're interested in. That's the blood that we tap into with an arterial line. And we can get more accurate reading of how much oxygen is in this patient's blood. Now, some of the terms you're going to hear are hypoxemia. Emia, of course, means in the blood, like anemia or hyperglycemia. So emia is in the blood. So hypoxemia specifically means low oxygen levels in the blood. This is slightly different from hypoxia, which just means low oxygen, period. So a patient's tissues may suffer from hypoxia, but the blood itself is hypoxemic. Low level of oxygen in the blood. The most specific term for that is hypoxemia. Why does it matter? Once again, this goes back to cellular respiration. If you don't have enough oxygen to accept the electrons of the electron transport chain, you cannot make ATP as fast as you need it. If you don't have enough ATP, that's going to mess up your ability to use a sodium-potassium pump. It's going to mess up your ability to make proteins. It's going to mess up your ability to fix the cell, and may end up in cell death. That's how much this matters. All right, now assessing the other gas, carbon dioxide, a non-invasive measure, there is none at present. We do not have a non-invasive way of detecting carbon dioxide. So if you're any kind of an inventor or know somebody who is, you might want to mention this. It would be really helpful if we had a non-invasive way to detect carbon dioxide. So we're stuck with invasive measures only. It's arterial blood gases, how much carbon dioxide is dissolved in there. All right, the terms that apply here with the carbon dioxide, it's not just low carbon dioxide that matters. In fact, it's high carbon dioxide that's a bigger problem. So the terms for these: hypercapnia, having too much carbon dioxide in the blood. This is usually, the biggest problem here is not ventilating enough. We're not getting enough air in and out of the lungs, so we're not able to dump the carbon dioxide well enough. Hypocapnia is a less common problem. It means low carbon dioxide levels in the blood, and it would be due to hyperventilation. This can happen during an anxiety attack. This is usually self-correcting. The old, breathing into a bag to concentrate carbon dioxide, that helps. If the person actually loses consciousness, then their breathing goes back to normal. And that's what I mean by it's self-correcting. So this typically does not need to be corrected. The hypercapnia may need some intervention. But I'll tell you, I'm kind of limited with the interventions there too. All right, so why does it matter, carbon dioxide? Why does out of range carbon dioxide matter so much? Is because it impacts the acidity of the blood. And the acidity of the blood impacts the way all of the proteins in the blood will work. because it can cause denaturation, it can cause changing of the shape of some of these proteins. So it's really important. So let's walk through what is the relationship here. There's no, blood pH, this is how much hydrogen ions are loose. There is no hydrogen ions in carbon dioxide. So this is what happens. Carbon dioxide and water can form a chemical reaction, and they actually kind of fuse together to form, so go with me on the numbers here. So you got H2, that's here, and then carbon, just got the one carbon, and then the oxygen, I have 2 from the carbon dioxide and 1 from the water, so that's H2CO3. That compound is known as carbonic acid. And it's called that because although some of the molecules will stay like this, some of them will fall apart, but not necessarily fall apart back into carbon dioxide and water. They can fall apart in this other way. And that way is one of the hydrogen ions falls off. And when we say a hydrogen ion, it's really just a proton. So this proton falls off, leaving behind the rest of this. So we took off one of the H's, and now we just have one H. We still have the carbon, and we still have all 3 of the oxygens. And because this hydrogen ion left its electron behind, that's where that negative charge comes from. All right, so we've got a hydrogen ion, and we have bicarbonate ion. These act as a buffer. These help stabilize the blood pH in case there are other things that are causing the blood pH to bounce around. So this is an important system in homeostasis. What happens when the carbon dioxide levels are out of range? When we have more carbon dioxide, so there's hypoventilation, we're not able to get rid of the carbon dioxide, we're building up carbon dioxide. That's going to cause more carbonic acid to form, which is going to cause more carbonic acid to fall apart. So we're going to have more free hydrogen ions in solution. That's going to make the blood more acidic. That's going to drop the pH. And if you need a way to remember that, drop acid, if you know that expression. So the more acidic it is, the lower the pH is going, drop in acid. The other side, the less carbon dioxide we have in solution, the more these things are going to come back together, reform to form carbonic acid, and then fall apart into carbon dioxide and water. So you're going to make less of these hydrogen ions. So less carbon dioxide in solution means less acidic blood. That's the importance of carbon dioxide levels. So let's see, all 3 of these aspects revisited again. Ventilation. We have talked about, mostly we've talked about regional hypoventilation, but there can be generalized hypoventilation, and I'll mention some examples. So let's see, the regional hypoventilation we've talked about so far: emphysema, acute respiratory distress syndrome. These are like, it's uneven, it's patchy in the lungs. Some alveoli are okay and some are not okay. But then there could be generalized hypoventilation, like for example, with a high spinal cord injury and there's damage in the medulla, that it's going to be controlling respiratory rate. That can cause just breathing to go down. An opioid overdose, that's going to depress respirations. If somebody's choking, all right, you get the idea. All right, so that's ventilation, air in and out. Perfusion is that blood going from the heart to the lungs, and we can get blocked blood flow through the lungs. This is what we call a pulmonary embolism. And then lastly, gas exchange. And some of the problems that can exist here are impairment of the diffusion across the alveolar capillary interface. Like for example, with pulmonary edema, there's too much fluid that's leaving the capillaries. So now where the alveolus used to be right up against the capillary. Now there's fluid in between. And so the gases have to pass through that fluid. Okay, and one more concept that we haven't mentioned yet is something known as ventilation perfusion mismatch. And so that we're going to have to look at the combination of the breathing in and out and the blood supply. And so this ventilation perfusion mismatch, I promise there's a whole other slide on it, but basically in a nutshell, regional hypoventilation. So there's some part of the lung that's not getting enough oxygen, but we're not adjusting the blood flow to that part of the lung. And I'll tell you about it in a second. All right, so let's take a look at ventilation perfusion match. Nobody calls it this, but in contrast to mismatch. This is the desirable state. When you have well-ventilated alveoli, you want all of those alveoli to be supplied with blood through the pulmonary arterioles and then the capillary beds that surround the alveoli. So here are some alveoli and pulmonary arterioles. This image, I ripped it off from a video that's in the additional resources. It's the osmosis one. It's on Cor Pulmonale. Highly recommend. All right, so here we have 3 alveoli, all of them well oxygenated, all of them have a blood supply. There is this way that this mechanism that our bodies have to match ventilation and perfusion like this, so that if there is hypoxia, if there's less oxygen here in this alveolus, that's going to cause hypoxic vasoconstriction. So in the smooth muscle that's in this arteriole, it closes down a little bit, increasing the pressure here and diverting more blood to the other places where there's more oxygen to be had. I don't know if this analogy is going to make sense, but if you've ever been trick-or-treating as a child, or maybe as an adult, and like this is the house that's given away toothbrushes or, I don't know, whatever, coupons or something that's not candy. Some of the kids are going to go, but most of the kids are going to find that house and go elsewhere. Yeah, so we're trying to match how desirable is this stuff with how much are we going to try to pick some up from there. Okay, so with a ventilation perfusion mismatch, that constriction doesn't happen. This is an undesirable state. We have a poorly ventilated alveolus or multiple alveoli, but they're still supplied with blood. So before I get to the rest of this, let's take a look at this diagram. We have less oxygen being supplied, but we didn't get that limitation in blood through there. So we're still going by there, which means that we're not going to, the blood that's being sent here, it's not going to be very efficient. It's not going to be able to pick up very much oxygen, and it's not going to be able to drop off very much carbon dioxide if there's not very good ventilation here. Over on the right is our textbook's attempt at illustrating this. So it's not as easy to see, but let's see if we can walk through it. So we've got 2 alveoli. One of them, you can see there's some mucus. So we're going to limit how much air can get through. The other alveolus has great air supply. In both cases, we have blood coming in from the heart, and the blood on the oxygenated side, on the well oxygenated side, is going to pick up a bunch of oxygen. It's going to drop off a bunch of carbon dioxide. This is represented by the very red color. On the other hand, this poorly ventilated alveolus, it's going to pick up some oxygen, but it's not very much, and it's not going to be able to drop off very much carbon dioxide. So that's where the purple color comes in. And so what ends up going back to the heart is a mixture of these bloods. So it's not as well oxygenated as you could have if you had limited the blood that's going by this poorly ventilated alveolus. All right, so that's the so-called ventilation perfusion mismatch. How are you going to treat a ventilation perfusion mismatch? Let's talk about the 2 problems. We've got hypoxemia. We don't have enough oxygen in the blood. And we have hypercapnia. We have too much carbon dioxide in the blood. For the hypoxemia side of things, we can increase the inspired oxygen, nasal prongs, face mask, they might have to be intubated. This may relieve hypoxemia in the ventilation perfusion mismatch, because even this poorly ventilated side, if you jack up the oxygen amount, you're going to get that to a normal level. The other alveoli will be super oxygenated. But at any rate, you're going to get well oxygenated blood, or that's the goal, is that you're going to have well oxygenated blood going back to the heart. Okay, so this is an unfortunate thing. There is no carbon dioxide vacuum yet. Let's go back to if you know any inventors, do mention this. This would be super handy to be able to have some way of removing carbon dioxide from the bloodstream, but at present, we do not have a way to do this. Well, ECMO, but a little less invasive maybe would be helpful. So carbon dioxide ends up being retained and can potentially contribute to acidosis, the bloodstream getting more and more acidic. And because the problem is in the lungs, we call it respiratory acidosis. So really the best way to treat hypercapnia is to treat the underlying disease, figure out what it is that's limiting the air going in and out of these tubes, and try to fix that. And then, support breathing as needed, possibly with ventilation. Okay, so gas exchange difficulties, what can get in the way of that is thickening of that membrane that the gases have to diffuse through. This can occur chronically, for example, in pulmonary fibrosis, or it can happen acutely with pulmonary edema or an infection of pneumonia. And once again, the treatment is supplement the oxygen to correct the hypoxemia. But again, we don't have carbon dioxide vacuums yet. And that brings us to the end of part 3. See you in part 4.